All right, good morning, everyone. Welcome to our third week. Yay.
Hi.
Let's see, third week. So yeah, 1, 2, 3. Just to help you all keep track of a couple things. So this is our third week. Then we'll have fourth week will be the first week of February. Fifth week will be this one, and then following that is our test. So it's on the calendar. It's about 1, 2, 3.5 weeks away. So I mentioned this not to scare you all, but just remember, stay on top of things because time will continue passing. The eternal march of time, right? And like I mentioned, if you all have started to kind of go through these things, if it's going smoothly for you and super easy, great. That is honestly not my expectation. My expectation is not that it would be easy and trivial, but that you'll have to spend time on it and things like that. So just know that if you're experiencing that kind of oh, this is tricky, that's normal. That's why I give so many practice problems and things of that nature. Let me give you all the joke of the day. Let's see which random one I pull out. All right, this one is going to sound poorly, but it's not. Despite the high cost of living, it remains popular. Living remains popular. That's the joke. Despite the high cost of living, it remains popular. Being alive. There you go. So, keep living. It's worth it, right? You matter. Regardless of how much it costs to feed yourself. Anyway. So, let me quickly kind of run through some of the main points that we kind of covered last time. There's one I'm going to reiterate. I've said this one I've already mentioned. We talked about electric fields. Fields cause forces. There's already a main point slide on that. So really the only thing kind of new we did is we talked about what if there's multiple charges. So if there's multiple charges, find the field due to each, and then do vector addition to combine them. If you have multiple charges, positive, negative, who cares what combination, who cares how many, you find the electric field in each of them, and then you find the direction, and then it's a bunch of vectors, and you combine them with the joy of vector addition. Remember that the electric field due to a point charge is kq over r squared, where k is Coulomb's constant, q is the charge, r is the distance from that charge to the point. All right, and then we also talked about inside of conductors, the electric field was 0 after the charges kind of settle, which happens almost instantly. They move very quickly. They redistribute very quickly. After that happens, the electric field inside a conductor is 0. Electric field inside conductor is 0. And the reason was, if it wasn't 0, then charges would still be flowing, moving. Specifically, and I'm even going to specify here, electrons. If there's an electric field, there's a force. If there's a force, a net force, then things accelerate, which causes things to move around. The electric field does not need to be 0 inside an insulator. E does not have to be 0 inside an insulator because the atoms, quote unquote, hold on to the electrons. So the electric field is pushing them, but the atoms are holding them there, so they're stuck. There you go. Okay, so that was kind of the main points from last time. I'll kind of try to do these as a recap at the beginning of each class of what happened before, and then these will be posted. So now what we're going to be doing in this class is doing some practice problems with it. We're going to do one practice problem on it. Oh, look at that. There's another one. Look at that. It was there, but you got to hear me say it. No, I'll leave them both. Can't hurt, right? So we're going to do this problem where we find the electric field at the top of this triangle. And then after this, I'm going to go ahead and front load you on this, and this is what your recitation activity is on this week. We're going to start building an integral. We're going to do our first problem involving calculus. Specifically, we're going to be finding the electric field. We did one charge. We're going to do several charges. And the next step is an infinite number of charges. And just like I said, how do you combine the electric field due to multiple charges? You find the electric field due to each, and you add them together. An integral is an infinite sum. That's all an integral is. An integral is adding up an infinite amount of infinitely small objects. That's what an integral does. So if we break an object into an infinitely amount of point charges, we can build an integral that will let us solve that. That's what an integral does for us. That's the tool. That's why we love integrals. They let us add up. If we can figure out a small piece of something, an integral can let us figure out the whole thing by integrating over the whole thing. The challenge is building the integral, and I have a nice little process for how to do so. So, let's go ahead and do this first problem, though. This question, I got a triangle here. Positive charge in the bottom left, positive charge in the bottom right, negative 2q at the top. In fact, you all, if you've done the problem set, you've probably already seen this picture, because this picture was also given, and I asked you for the net force on negative 2q. This problem is not asking for the net force, it's asking for the net electric field where 2q is located. So the question is, at this point, what is my electric field? That's the question. That's step one. What are we solving for? Step two, the picture's already drawn for us. We don't need to add anything to the picture. It's all there. We have the sides of the triangle, we have the charges. Everything's beautiful. There's no numbers in this problem. I don't tell you the value of A, I don't tell you the value of Q. This is one of those problems where we work purely in variables. And if you happen to know the values of them, you could plug them in and get the exact value. But in this case, we don't. So, net electric field at the top. How do we do this? We're going to label our charges. 1, 2, 3. 3 charges. It's nice to label them, helps us keep track. We're going to find the electric field in each of these charges at that dot, and then do math from there. So, charge 1 is going to make an electric field at this dot. Positive charges make electric fields that point away from them. That's a definition of electric fields. They point in the direction a positive charge would move, and a positive charge would move away from positives. Yay, we can chat about that. Great, there's E1. E2 is going to point away from E2, or from charge 2. Up to the left. Charge 2 is in the bottom right. It's going to point away from that. Charge 3 does not matter. Charge 3 does not make an electric field where it's located. We chatted about this. You cannot make an electric field where you're located, otherwise it would affect yourself. That charge would move itself. It doesn't make sense. And we also remember when we get to the equation, we're going to see mathematically. But charge 3 here doesn't matter at all. And we chatted about that last time. Every problem I gave you all a couple of these. I just pretended that there was a charge there and it changed nothing in the problem. So if there's a charge at the point we care about, doesn't matter. Ignore it. So, if I want to get E net, I'm going to need to add E1 and E2. And this little thing I'm drawing above the arrows is the vector symbol. It's like an arrow, but it's missing the bottom part. It's just easier to draw, I guess. I don't know. You can put the arrow if you want. That's the same notation. If we want to do this, remember to add vectors, we're going to need to break into x and y. So we're going to need the x component of 1 plus the x component of 2. And then for the same thing for the y direction, we're going to need the y component of 1. Now, at this point, I have not acknowledged directions. I haven't done positives, negatives. I'm just baseline. Hey, here's how we add vectors. Add them, break them into components. Great. We're going to put the positives and negatives and all that kind of stuff as we do this. But for now, I'm just kind of straight up showing you, hey, we're combining vectors. Now, E1, we've talked about it's breaking it into components. Classic. We draw this. So here's E1. I'm going to move this E equals question mark over here. If I want to break this into its components, I'm going to draw a beautiful triangle. There's my triangle. So nice. This is the x component of 1. This is the y component of 1. We need to know that angle. It's going to be in class and figure out angles. How do we figure out that angle? That angle is the same as this angle. Why is it the same as this angle? If I took this arrow and I moved it down here, they line up with each other. So you can see it's the same angle. You can move kind of vectors around to kind of help you see angles. I'll give you all about, this is just a good exercise. 20 seconds, see if you can figure out the angle. Don't shout it out, just think about it. See if you can come up with it before I tell you what it is. This is one of those you need to be good at. All right, the answer is 60 degrees. Why is it 60 degrees? It's an equilateral triangle. All triangles have 180 degrees. Divided by 3, it's 60. You all need to get really good at figuring out angles from pictures. Like, that's a super important skill that we're going to keep practicing. It's just a thing you need to be able to do. All right, so if I want the x component, in this case, the x component is adjacent, so I'm just going to multiply that by cosine of 60. Now, it's positive because it's to the right. Awesome. And down here, if I do the y component, it's going to be sine, not because sine is always the y component, but because sine here is the opposite side. Great. And it's positive because it's up. We're going to repeat the same process for 2. Turns out that this is also 60 degrees. There's a beautiful triangle. And so we're going to get here a minus sign because it's to the left. And down here, we're going to get a positive because it's up. Sorry, it's not up. Up. That's correct. So, great. We're building our math, building the equations. This is the process you go through, vector addition, all that good stuff. And then at this point, the only thing left I'm going to tell you is really simply, how do I find E1? It's going to equal, remember the equation for the electric field is KQ over R. So this equals KQ over R. So in the case of E1, that's going to be Q1 over A. In this case, it's just Q. I'm going to put that on do not disturb, and I'll try to call him back later. I think it's right on do not disturb. All right, great. So you're going to plug those in. Plug back to E2 is going to be the exact same thing. So and you can actually see it from our picture that the x component is going to be 0. But mathematically, you can prove that for yourself. I'm going to try to mention this when I do this. When I sometimes have 0 by itself, I'll put a line through it just so you don't think it's no. It's just that there's nice little things I'm going to do that you might have seen other instructors doing, but this is one of them. If you ever have a 0, sometimes it's useful to put a line through it so you know it's a 0, not no. Another thing is when you write a 7, sometimes my 7s can accidentally have a little tail. How do you know it's a 7 and not a 2? I put a line through it like that. Just nice little notation things. Another thing is that when you do a Z, that can sometimes also look like a 2. Put a line through it, and now it's a Z. These are nice little just notation things. You don't have to do these, but they're going to help you out. So, there you go. The rest of it is just plug it and chug it. You're going to end up with the final answer when you plug in what sine of 30 is, or sine of 60, which is going to be square root 3 over 2. Plug it in, do the math, and you'll see. But I'll leave that step for you. I won't do all the things. The last step's pretty simple. So, try this out. Remember, every single problem I do in class, probably a decent problem to do. There's a lot of skills there I choose for a reason. And make sure you solve them completely. Don't just get to this point and say, oh, he didn't finish it, so I'm not going to finish it. No, go through the whole thing. The only reason I don't solve through the whole thing is, 1, I want you to try it. 2, for the sake of time. I got 50 minutes with you all each day. It ain't much. Okay. So, that's how you, if you have any number of charges, this is what you do. 15, 20, whatever. So now we're going to move to continuous charge distributions, specifically where you have, so the example here is going to be, I have a line of charge. I have a rod, and it's charged. Find the electric field at some point above it. It's not a bunch of dots. It's a rod filled with charge. This is the real world. Okay, all worked out. If you're like, what's going on? Here's a message. I'm one of the lab coordinators, and so when things don't go well, people reach out to me, and you have to see it. But it works itself out. Yay. So this is a problem. And what I'm going to convince you all of, what do you do when you have a bajillion things like this? We're going to pretend like it's an infinite amount of tiny charges. Infinite amount of them. I know I'm drawing them. Imagine I could draw them infinitely small. Obviously I can't. And this is where calculus, I'm going to start bridging calculus and physics. You all have done derivatives. You all have done integrals. You all have seen symbols, but now we're going to make physical meaning with them. So this is my equation. E equals kq over r squared. What do we call a q that's infinitely small? We're going to turn this. If I want the electric field to do one that's infinitely small, it's going to be k. Instead of a q, I'm going to put a dq. What does dq represent? A infinitely small charge. Anytime in calculus you start as dx, dq, dy, that just meant an infinitely small x, infinitely small y. And when you did an integral, you were adding all of those contributions up. So this is the physical meaning. dq here means this little charge here has a value of dq. That's its charge, dq. Each of them has a dq. They're all infinitely small and infinitely same size. And if I draw a picture here, which I already did, that's r. R is the distance from that dq to that point. Now the problem is, this r is not the same everywhere. That one's r. Let's call that one dq1, and we'll call that one r1. Let's pick another random charge over here. This one would be r2, and this would be, dq2. Every single charge has its own r. So r is not a constant. What does that mean when you integrate? You cannot pull it out. You actually have to integrate it. And last thing I want to point out here, this field is not the entire field. It's not E. It's not the entire field. What is it? It's an infinitely small part of the field. What is that infinitely small part? dE. Putting that D in front of it makes it an infinitely small thing. So all of this logic I'm trying to explain to you is to help you to understand when we get to the process, why we're going to do the process we're going to do. One more thing I want to mention, each of these is a vector. If I drew it, so these I made them negative, whatever, that's fine. This electric field is going to point towards a charge. This is dE1, the electric field due to the dQ1. Charge 2 over here is going to point down. These are vectors. What does that mean? We can't just do a single integral. We need to break that integral into its x components and its y components. You can't just add up vectors willy-nilly. This one's 3 and this one's 5. I can't say 3 plus 5. Can't do it. What do you need to do? You need to make an integral for all the x components. You need to make an integral for all the y components. How do you make an integral for all the x components and all the y components? The same way we did this problem. How do we break it into x and y? We started with the original, 1 plus 2. You then broke it into the x and you broke it into the y. How are we going to break things into x and y? The same way we did this one. Multiplying by cosine or sine respectively. It's the same process that we've been doing, but it's going to be in an integral form. And the last thing I'm going to kind of mention to you all, and I keep saying the word integral, how do I get the total field? I integrate both sides. If I integrate dE, it turns into E. If I integrate the other side, it turns into the answer. Now, I will tell you that a lot of these problems, the integral will be disgusting. I'm not going to actually have you solve the integral a lot of times, which is the interesting part. It's actually quite difficult for me to make problems where the integral is something that's pretty quick to solve. It's not too bad for me to make an integral that might be straight sub or things like that. But rule of thumb on the test, you should be spending 70 to 80% of your time doing physics and only about 20 to 30% of your time doing math. And I designed the problem accordingly. You're not going to spend most of your time doing math, solving an integral. You will spend most of your time building the integral. So, for example, when I post the practice exam, you are going to see I have a question like this, and the question wasn't, what's the electric field? It was, what's the integral for the electric field in the y direction? Build the integral, that's all I want. You don't actually need to solve it, because solving it would be gross. So, there is a couple here there, but boom, there you go. There's the equation. our hat just, again, we kind of use that, shows us the direction, but we're not really worried about too much. There's a couple steps, there's a few steps we're going to need to do. We're going to need to get DQ in terms of spatial coordinates. I can't just integrate over DQ and call it Q. I can't. Because why? Because R depends upon the Q, so I need to get it in spatial coordinates. You won't have to integrate it in space. That's all you need to count 1, 2, 3. You won't integrate over X, Y, and Z. We're going to do the same thing here. Integrating over space makes sense. Integrating over this charge doesn't really make sense. We get it in terms of space. And then we're going to need to break it into X and Y. And then one last thing we're going to need to do is we're going to need to get everything in terms of one variable. You'll see what I mean as I solve this. This will make more sense as we kind of do one of these problems. So, before we kind of do a problem, I'm just going to show you some hypotheticals, and then I'm going to tell you the only ones we're actually going to do. So there is different ways to spread out charge. It's not going to really be relevant for a little bit. For this, we're just going to do a line of charge. A single 1D line of charge. There is also a 2D plane of charge and a 3D sphere, or like you can have 1D, 2D, 3D basically. A 1D object, a 2D object, and a 3D object. 1D is a single line. That's my line of charge. 2D is a sheet of paper covered in charge. 2-dimensional. 3-dimensional, it could be a sphere, it could be a cube, it could be, a 3-dimensional object. You all see 3-dimensional objects. Okay, we need to express how this charge is spread over space. Remember, we can't integrate this over DQ. We need to get spatial coordinates, X, Y, Z, that kind of thing. How are we going to do that? We're going to use density. Density gives us a representation of how things are spread in space. If you all remember mass density tells you how your mass is spread over space. We can do the same thing with charge. So this symbol here, I'm going to kind of go through each of these symbols. This first one is lambda. This is lambda. Yeah, it's also used for wavelength of light. Lambda here, you're like, it's useful for me to teach you all how to draw this. It's very unlikely you've drawn this symbol before, unless you've done physics. What I kind of do is I do this little arch thing, and then I give it a leg. It's one of those just when my daughter is 3.5, teaching her to do her letters, things like that. You got to actually show that if you want to draw them nicely, it's nice to do that. So yeah, you do this little swoopy kind of thing down, and then you give it a leg. So that's lambda. This is for 1D charge distribution. So if I take the charge and I divide it by the length, that tells me how my charge is spread out, assuming it's a uniform charge distribution. If you're like, whoa, where's all this coming from? You all remember, hopefully, from chemistry, density is mass over volume. That's 3-dimensional. If you want 1-dimensional, replace volume with length. And we're not working with mass, we're working with charge. So that's the logic here. Okay, so that's lambda. The next symbol is sigma, which I kind of start and then give it it's an O, but it has it keeps going to the right. So this is sigma. It's lowercase sigma. You all have seen capital sigma. This is capital sigma. It's for some. You are going to learn a lot of Greek letters because there's only 26 letters in the English alphabet, and even with the capitals and lowercase, we don't have enough for all the equations and all the variables and all that stuff. So that's sigma. That one is charge over area. This A stands for area. This L stands for length. We're figuring out, these are just useful things. We're only actually going to use the first one for today, but these other ones are going to show up next week or later this week when we get off as well. So it is things we need to know. And the last one is a typo that somehow I haven't fixed. If you notice this, you're like, why does that one also say A? That should be a V. Charge over volume. That last one is rho. You have seen that in chemistry. It's the exact same one that we use for density for mass. Rho here is a P, but normally a P that you put this little straight piece here. Rho is kind of a italicized one without that little up thing. So you just kind of draw it in an angle and you don't put the up thing. R-H-O is how we, I guess, phonetically pronounce it. These are all Greek letters, so lambda, sigma, and rho. There you go. 3 new letters for you. We're only going to focus on the first one today, but we're going to use the others later. They're going to be important. So, our end goal, our goal is to get Q in terms of spatial coordinates. That's our goal. So like these next two bullet points are going to talk about that. We can see lambda in the problems I'm going to give you all. I will either give you lambda as an equation. I'll say lambda equals 5x, lambda equals 5x squared, whatever. Or I'll say it's uniform, which is a fancy way of saying lambda is a constant. It's a value of like 3 or 5 or 6, or it's a number. So lambda in this case is going to be a constant. With that in mind, I'm just going to write exactly what I did here. I'm just going to do it real quick. So lambda equals Q over L. Rearrange this for Q. Q equals lambda times L. Now we're going to take the quote-unquote derivative of both sides. Get an if I turn Q into an infinitely small part, instead of a capital Q, it becomes a little q, dq, tiny, 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 tiny piece. Lambda is a constant, so we're not going to actually take the derivative of that. That's going to kind of get pulled out. But the L is not a constant. This is the thing, this is the length of it. We're going to go over the whole length of it. And then the last thing you have to do is just replace L with what makes sense. If your rod is going left, right, so for example, if your rod is doing this, then dl is going to turn into dx. You're not going to integrate over y, you're going to integrate from left to right. Our goal is to add up all these pieces. Add up all these pieces, and let me just even show you this. Here's my little tiny charge, dq. What's the value of this tiny little charge? It's lambda times dx. If I multiply lambda by how big this is, how much charge do I have? dq. If I want a tiny piece of this, if I want to say how much charge is represented here, I take the charge density and I multiply it by how much length I have. This is the same way that mass works. I wish I had like a foam ball or something, but I don't. Oh, actually I do. It's so convenient. This foam ball. If I ripped a piece of this foam ball off, I'm not going to do it because it'll break the ball. If I ripped a piece of this foam ball off and I wanted to figure out how much mass was in it, how would I figure out how much mass was in it? I would take its density and I'd multiply it by the volume of this tiny little piece, and that would tell me how much mass I have. If I want the charge, I take its density and I multiply it by how much I have, the length of it. That's the idea here. That's the logic. Yeah, so if your rod is left-right, you're going to make dl dx. If your rod is up-down, you're going to make it dy. Integrate, up-down, y. Left-right is x. Z, I guess could be in and out, but I'm not going to do one like that because that'd be hard to draw. So this is the idea. We're building our integral. We're changing dq into something we can actually integrate. Good? Okay. So now, we're going to go ahead and go through the problem on this. And then after I go through this problem, I'm going to show you all I have a PowerPoint slide that kind of walks you through step by step the decisions I made. But yeah, we'll just do it first, and then I'll have it nicely written in a 1 step, 1, 2, 3, 4, 5. The steps I'm doing this. Find the equation for the electric field, a distance z, above an infinite line of charge that carries a uniform charge density of lambda. So the charge is evenly spread over this rod. It doesn't specify this rod. So this rod we're going to say is left to right, because I can say, it doesn't say, but that's what it's going to be. So I got a rod of charge. It's a nice, infinitely thin rod. Charge goes forever to the left, forever to the right. And I am asking for the electric field at some point a distance z above it. What's the electric field at this point due to this infinite amount of charge? It also doesn't specify, but I'll go ahead and make this. So I'll go ahead and do this. We'll make it a positive charge. Positives are generally easier. Negatives would just be the opposite answer. So this thing is covered in negative charge uniformly throughout the entire object. Positive, 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 throughout the entire object. Okay. So, how are we going to do this? Oh, look at all those positives. Forever and ever and ever and ever and ever. I don't want to keep drawing. Okay. First thing we're going to do, we drew a picture. We're going to add a couple more pieces to our picture to make this easier for us. We're going to pick a little tiny piece of charge here. Little tiny piece. We're going to call it dq. Little tiny piece. If we understand one piece, then we can use it to understand all the pieces. Why are we going to do this? We have our dq. Anytime we're talking about electric field, we care about the distance. This is r. R is the distance from that charge to where I'm finding the field, just like it's been up to this point. Nothing new here so far. The only change I made is I made it a dq instead of a q. So we have one little piece, and we're going to see how this picture is super important. You should always, when you're kind of doing these problems, draw a little dq, draw what r is. It will help you. You will see what I mean as I solve this. So now we are going to, if I want the electric field due to this tiny, tiny little piece, it's going to be k dq over r squared. Now we know that we're going to integrate both sides. So it's going to turn into E equals the integral of k dq over r squared. This is kind of where every one of these problems starts, is with this integral. This is due to one tiny piece of charge. Integrating it will give us all the charges. And now we're going to go through that process I mentioned. We need to get dq in terms of spatial coordinates. How are we going to get dq in terms of spatial coordinates? The way I just outlined. Remember that lambda equals the capital Q over L. That's like the definition of lambda. And through that, we then derived on the last slide that therefore dq equals lambda dl. We chatted about that. We just, take the derivative, make q really small, make l really small, lambda is a constant. If you really want, you could kind of even write this like this, dq over dl. Because it's uniform, if I take the entire charge and the entire length and I divide those, I get lambda. If I take a tiny piece of the charge and a tiny piece of the length, I still get lambda. And the same way with the foam ball. If you all wanted to find the density of this ball, what would you do? You take its mass, you divide it by its volume. What if I only had a tiny little piece of this ball? I would take its mass, I would divide it by its volume. It's really tiny, it's dm, its volume would be dv. D just makes it really small. That's all it represents. Okay. So now we plug that in. We're just going to kind of plug in each step. So the integral of k lambda dl over r squared. Now, L is not one that we're used to taking derivatives of. So let's change it to one we are used to. This rod is left-right. So I'll give you all 20 seconds. See what Cartesian coordinate, that's a fancy way of saying x, y, or z, that we're going to integrate over. Spend 20 seconds if you can figure it out. It's not a tricky question. We're integrating from the left to the right. We're integrating over this rod. We're getting a tiny piece, and the next tiny piece, and the next tiny piece, and the next tiny piece. That's in the x direction. So this is going to be the integral of k lambda dx over r squared. Okay? Now, we need to define something that's probably useful for us to do. Definitely useful for us to do. We should define, if we're going to integrate over x, we should probably know where the origin is. Anytime you all integrated, you need to have a reference. You need to have a reference frame. It's a fancy word of saying, where is 0, 0? Where is the 0x value? And we're just going to pick right here. We're going to pick where we started. This is 0, 0. This is the origin. It's where I started. You're going to see why this is a useful place to pick in just a second. So I mentioned this before. So far we're doing great. K is a constant. Lambda is a constant. So actually we're just integrating dx over r squared. R is not a constant. R is not a constant. Really easy to prove that. Pick another random dq. Oh look, it's r is a different value. You can just see that if you pick any other charge in that picture. It's not a constant. So now, I'm going to have you all spend about 30 seconds or so, maybe a minute even. So much time. Get r in terms of x and another constant. You all can do this based on the picture. You have the abilities. I want you all to try to get r in terms of x and another constant that's given in this problem. Try it out. Work with people around you. Give you a minute.
The most legitimately is this. Not bad. I mean, like, the house is and I'll do the 3 year where
All right, so the key to this is adding x to our picture. What does x represent? X is a measurement. What is x a measurement of? The horizontal distance from the origin. X is the horizontal distance from the origin. There's my origin. What is x a measurement of? It's from there to the point that I'm getting the charge. X is from the point on the 0 to where I am my dq. So this line here is x. X changes. That's why we're integrating over x. Depending on where my charge is, x gets, bigger, smaller, depending on where I'm at. That's the whole point. We're integrating over x. So as my charge moves closer to the origin, x gets smaller. As I move farther from the origin, x gets bigger. This is what we're integrating over. So, if you look at this, oh look, a triangle. What is the value? How do I get r? R squared is going to equal x squared plus z squared. Because it's a triangle. That's it. So you're going to replace r squared with this. If it was just r, you do the square root of it. Normal Pythagorean theorem stuff. So, to continue this, so e is going to equal the integral of k lambda d. You know what? Let's make this a little easier. We can pull out k and lambda. We don't need them in the integral. They're constants. Let's just make it a little prettier. Square root of x squared plus z squared. And at this point, we have one more step that's very important that we have not done yet. There's only one more step we need to do before we can solve this integral. Start solving this integral. This is not in components. This is a vector. Which way does this vector point? So that's just the one tiny piece. That's one tiny piece. So how am I going to break this into components? The same way I did before. Yeah. Oh, thank you. I need to get rid of that. I'm so used to it. Yeah, thank you. It's squared, so that goes away. Good catch, good catch. No square root. No square root because it's squared, so it goes away, so you spare that. So this is the net electric field now, but I am not, this is addition. I am not allowed to add vectors that are not parallel or anti-parallel. You must break it into x and y. So I'm going to take this beautiful picture that we've drawn. At this point, we haven't even read the problem anymore because our picture had everything we want. That's where you want to get with your pictures. You want to get to a place where I don't need the problem. Like that's the problem. It has everything I need. I don't need the words anymore. All right. You all need to break this into its x component and its y component. I need ex. I need ey. How am I going to break it into x and y? The exact same way we broke this one into x and y. Angles. That's the way I'm going to teach you. There's a kind of another way with the arhat vector that I won't get into because it takes too long to teach. It's a bit better in some ways, in a lot of ways, but this will do the job for you all. And continue to enforce this angle kind of method. So, we do the same thing. We're going to draw. Again, our picture is so important. If your picture stinks, your problem is going to be terrible. I would like this angle. Oh, what does that angle equal? Oh, that angle. Okay, how would I break this into x and y components? If I made, a pretty little triangle, we're going to get that the x component is going to be k times lambda times the integral of dx over x squared plus z squared times, in this case, the x component is the adjacent side, so cosine of theta. The y component, same thing. K lambda integral of dx Now, this is a habit I see. I'm going to mention this now because I see this all the time. People go to the y component and they sporadically try to change dx to dy. This y component does not mean changing dx into dy. You're always integrating left to right. You're always integrating over x. The y component means that I'm taking that vector, that electric field vector, and getting its y component. Do not replace this dx with a dy. This rod doesn't go up, down. There is no y component of this. So it's just, think about that more if you're unsure what I'm saying here. That's a good thing to think about. It's still dx. It's still dx. What am I doing to this? I'm multiplying it by sine of the angle. Now, here's the concern. This angle changes. I cannot leave this angle as it's not a constant. Why is it not a constant? Literally pick any other triangle and you're going to see that that electric field goes up or down depending on what charge you pick. You know, if I picked a charge really close, it's going to make an electric field that's really steep. So, another nice little minute exercise for you all. Get theta in terms of x and other constants. Try it out. You can only integrate it if it's all in terms of one variable in the constants. So get theta, get cosine theta in terms of x and other things.
I'm just gonna make my body shut down because the pressure is crazy. Yeah, I guess we are. What the hell? Oh, Florida is so weird. It's really weird.
All right. Now, we're going to go ahead and do this. Before I do this, I'm going to mention something. This x component, I'm going to go ahead and draw a charge on the other side so we can see something before I start solving this. If I picked another charge over here, another dq, that one, and in fact, let's use some beautiful symmetry. We love symmetry in physics. Let's pick a dq that's exactly the same distance away as the other one. All right, there's my little dq, there's my dE. We have some beautiful symmetry here that's going to make our life easier. I have a charge on the left that makes a field to the right. I have a charge on the right that makes a field to the left. The size of those areas is the same, the angle is the same, so what's actually going to happen to the x components? They're going to cancel and equal 0. In this problem, the x components cancel because one's to the left and one's to the right. So, in this case, we can replace the cosine, but I'll tell you this one's 0. Technically, if you wanted to solve this one, you would even break it into two integrals. An integral for the left side of it and an integral for the right side of it to account for that positive and negative. Remember when you're adding vectors, right is positive, left is negative, so you'd actually have to split it into the positives and negatives if you wanted to do this. I'll write that out in just a second, but the punchline is it's 0, the x component. The y component, let's look at that one. Let's do the sine. We're going to use the same, if you're like, what are you supposed to get cosine? Sine's going to be the same exercise. SOHCAHTOA. If you all don't have number at SOHCAHTOA, get a tattoo of it or something. It's worth remembering. Sine of theta is opposite over hypotenuse. What is the opposite? Z. Opposite over hypotenuse. That is Z over R. If only we knew, but R changes. If only we figured out R in terms of x and another constant. So this is going to be Z over the square root of x squared plus Z squared. Why? Because we had Pythagoras theorem. So long story short, this is going to be k lambda integral of dx over x squared plus z squared times z over the square root of x squared plus z squared. And my final integral that we would actually solve would be the integral. You could pull out the z if you wanted to. I'm just going to leave it in here. It doesn't really matter. It's a constant. Square root, not square root, x squared plus z squared to the 3/2. That's the integral. Are we going to solve this? No, I don't want to do it.
Me either.
How would you solve this? Trig sub. You always solve this using trig sub. It's not a nice integral because it'd be nice to get an x on top. You don't, so it's unpleasant. This would require trig sub. If you want an extra Calc 2 practice, it's good to do it. Trig sub is one of the few integral skills I still remember from Calc 2, like Taylor series, all that stuff. I know I learned it. If you asked me to do one, it's been a little while. I should probably know how, but I'm a little rusty. Last thing we need to put on this integral. Anytime you all integrate, you need bounds. You need a left and a right. So what are the bounds of this integral? I'm integrating over x. Where is my leftmost x point on this picture? You can just shout out. Negative infinity. Where's my rightmost x point? This is the final answer. That is the answer to this problem. What is the electric field made by an infinite line of charge with a uniform charge density? It's this. K lambda integral of z dx over x squared plus b squared all to the 3/2 integrated from negative infinity to positive infinity. What is this a lot of steps? Yes. Do you need to know how to do this? Yes. It's going to look like a lot of steps because I took my time with it because I'm trying to help you all understand the process. But in reality, this is about 3 or 4 lines. It's not actually that many lines. This first step, I went in like painstaking detail, but you can do this in about 3 or 4 lines, not too bad. Yeah. Yeah, great question. This down here was to the power 1, and then the square root was to the 1/2. It's a small thing, but it's a good question. I appreciate you asking that. Just to show you all this one real quick, if I actually solved this one here, I would need to break it into 2 integrals. I would integrate from negative infinity to 0. And then the cosine would have turned into x over r, whatever. Sure, I'll put it in the square root. X squared plus z squared plus the integral from 0 to infinity of dx over x squared plus z squared. The same exact integral. And if you actually did those integrals, they would cancel out mathematically. Mathematically, they would work out. Oh, there's supposed to be a negative sign here. There you go. All right. But you don't need to do those integrals to prove that. Just look at the picture and you can say symmetry. Physicists love symmetry.
Is that open parentheses there?
Open parenthesis. Yeah, let me close that out. Boom.
Okay.
Yeah. So let me show you all the summary slide on this. So infinite charge, look there, it's all written out, whatever, and sort of thing. This will get posted if you're like, that was so much, I missed it. I'm going to post this. Oh, yeah, go for it.
Yeah.
Let me show you all the summary slide, and we're going to do one more problem on this on Wednesday. Your recitation, if you have your recitation today, it's going to be doing this problem as well. So it's going to be more practice on this because it's something you all need to know. We're going to do a ring of charge. All right, let me show you all the nice little summary that's not, oh yeah, there it is. So, I should really make this step 1, 2, 3, 4, 5, but whatever. Draw a picture with a charge, like the charge distribution. Make a dq and make an r, just like you did. Oh look, there's the picture. Write dq as charge density times dl. In our case, lambda times dl. Write dl in terms of dx, dy, dz. We're going to see this one here next class is already data. We'll see it next time. Replace, we're not going to do the r hat one. I'll update this to do x to cosine. I don't know why I put the r hat. This is one option. It's a bit more rigorous. I'll replace this with a cosine and sine that we did today. This is another way. In fact, I'll probably leave both. And then get everything in known and solve. It's what we did today. Get in known variables, break it into x and y, solve. That's the punchline. That's what we did. A lot of steps, but it's something you all need to do. This is learning how to build integrals. Not just solve them, but build them. That's a new skill for you all. All right. Have a good one. I'll see you all Wednesday.